We're good.
My name is Brian Jones. I'm going to give you a presentation on 6 different forms of corrosion. These forms of corrosion that we're going to be going over are going to be hydrogen blistering, hydrogen embrittlement, hydrogen-induced cracking, stress corrosion cracking with a neutral pH, stress corrosion cracking with a high pH, and sulfide stress corrosion cracking. Now, all of these are forms of environmentally assisted corrosion. And you'll notice a lot of these look very similar to each other, the way they happen and the way the mechanism works. And it's got a lot to do with hydrogen. So we're going to get straight into it. The first one is hydrogen blistering type of environment. It's found in mostly refinery type environments with high temperatures, moist atmospheres. External factors that are going to affect it's going to be heat and moisture. Like I said, in the moisture, what it does is it brings out actual hydrogen atoms in the atmosphere. They're just going to go down and get these low strength steels, which are the ones that it affects. Now you can see here the picture, it's maybe a little blurry, but you see the nice little pronounced blisters on this piece of steel. And I'll show you why it does now. Again, the mechanism, basically what that says is there are hydrogen atoms that come from the atmosphere and even some on the pipe that go down into impurities and voids inside the steel pipe itself. And what they do is they collect in a pocket, and we'll show you that in this mechanism picture. It'll make a little more sense whenever I'm explaining. See, the hydrogen atoms are going to go in this void here, and they're going to form together and make a hydrogen gas molecule. And the molecule gains pressure, and it's going to bow out and make these blisters on the pipe. And you can see that. Go in the void, hydrogen atoms go and form a hydrogen gas. I don't know what the laser doing. For testing and monitoring, a way to test for hydrogen blisters is going to be using a hydrogen probe. It's a pretty standard way to do that. Prevention is use of coatings that are very resistant to moisture, like plastic and rubber. And then you can also use inhibitors. Those are generally used in closed cycle systems. So something you can think of a closed cycle system would be like a radiator in your car. Material substitutions, you can use any material that has more nickel in it, because the nickel has a less chance of diffusing the hydrogen, like getting down into the metal. Next, we're going to talk about hydrogen embrittlement type of environment it's found in. It's also kind of a refinery environment, but where it has lots of moisture and like it can be uncontrolled CP. Any source of hydrogen is going to be a problem for you in any kind of environment like that. Metals affected, generally high strength steels, like titanium alloys and stuff like that. These are just really strong metals, and that you can imagine have a high carbon content because they're strong. A formula for hydrogen embrittlement is here. I'll be honest with you guys, I'm not really sure what all those little letters mean, but this is what the industry uses to determine it. External factors are room temperature. Room temperature is bad for hydrogen embrittlement because the hydrogen is easily diffused in the metal at that temperature range. Mechanism. Hydrogen diffuses along the grain boundaries with the carbon. It combines with the carbon to form a methane gas inside of the actual structure. And then that methane gas, kind of like the blisters, it's got nowhere to go, so it forms gas and it's going to crack. And you'll see that kind of goes along with hydrogen-induced cracking, but that's also what makes the metal brittle. And then for a mechanism, you've got 3 things that really are going to affect this. You've got metal susceptibility, so you've got those high carbon steels, excuse me. You got a hydrogen source, so the moisture in the air or your CP. And you've got mechanical stress, so you've got stress on that metal that's going to cause that embrittlement. The biggest cause of it is the material susceptibility. And these 2 things down here, the hydrogen source and the mechanical stress, are going to be your triggers. Testing and monitoring. basically that says they're gonna do a step loading test. That big, long standard, that's what they use, a step loading test. Prevention, you're gonna mitigate the atomic hydrogen. So you're gonna try to keep it dry, you know, get the hydrogen away from it. You're gonna use clean steels, or killed steels is what they refer to them as, instead of rim steels, because this decreases the porosity and the voids that are internal to the metal. You can also bake the steel by heating it to 200 to 300 degrees Fahrenheit, which helps get rid of that hydrogen. And then you can again use alloys with nickel because of the low hydrogen diffusion rate. Next is going to be hydrogen-induced cracking. This is going to sound familiar. I want the hydrogen brittlement and the blisters because they all have really similar properties. This type of corrosion is also in fire environments. Steels that have a hardness of 22 or more on a Rockwell C scale, that's pretty hard metals like titanium alloys and high-strength steels. External factors, temperature plays a large role in hydrogen-induced cracking. Like hydrogen brittlement, room temperature allows permeation of the hydrogen through the metal. Mechanism. There is no definitive mechanism for hydrogen-induced cracking. They say there are several things that make it happen. Talking about the crack tip and the competition of the hydrogen atoms bonding with the lattice in the metal. A picture might explain it a little bit better. And you can see up here, you've got your water vapor and your electrolyte, and your H2 gas is going to go into the crack tip. And you're going to have stress, like that hydrogen embrittlement. You have stress in the metal. And then you're going to have the internal hydrogen stress is driven to diffusion. And that's what's going to make it crack open through the lattice. Testing and monitoring. The conventional method of detecting wet H2S cracking is wet fluorescent magnetic particles, which has the ability to detect subsurface cracking in steel caused by hydrogen-induced cracking. Prevention, you can preheat, post-heat, or use nickel alloys. So all the hydrogen type corrosions or defects in the metal, you're going to use like nickel because of its hydrogen diffusion rate is lower. Stress corrosion cracking, or in neutral pH, sorry. Environment. This is going to be in groundwater with a diluted groundwater with dissolved CO2 that's in there with which is, the CO2 is caused by decaying organic material. So dinosaurs, old plants, dead bodies, whatever. You know, it's just something in the water that's causing the carbon dioxide to come up and dissolve. Susceptible metals, stainless steel and aluminum. External temperature, external factors. Temperature doesn't really have a role in this so much because, sorry, I lost my train of thought. Temperature doesn't have much to do with stress corrosion cracking and neutral pH, but it can be said that colder environments can produce more dissolved CO2, which could make it problem worse, but it's not a direct effect on it. Mechanism, there's no unified mechanism for stress corrosion cracking, but the joint action of three things: a susceptible metal, the appropriate pH, which in this case is going to be from 6 to 8, and tensile stress. And you're going to see this in the illustration I did. You have a reactive environment, which soil is one of them here, and your pH is going to come from your soil. Coatings, cathodic protection, all these things are going to give you a reactive environment. Your susceptible metal. So if your material is susceptible to it, that's going to play a role in it. And then your tensile stress. And all these things come together and they create stress corrosion cracking. And this is going to look really familiar to you guys with high pH. So testing and monitoring, you can use smart pigs, which you guys know you can go and check the internals of the pipe. So indirect assessment. You have hydrostatic pressure test. We're going to load up the line with water and pull up the pressure and check your cracks. And then you have direct assessment, so bell hole examinations and things like that, where you can get in and actually look at it. Prevention for it is going to be CP. stress corrosion cracking with high pH environment. It's going to be a groundwater bicarbonate solution with a high pH and elevated temperatures. Susceptible notes: carbon steel, high strength steels, austenitic steels, high nickel alloys actually, and brass aluminum alloys. External factors are going to be temperatures greater than 40 degrees Celsius are necessary for the high pH stress corrosion cracking susceptibility. pH window for high pH stress corrosion cracking is 9 to 14. So it's very basic. Mechanism. There's no unified mechanism for stress corrosion cracking, but it's affected by three things: susceptible material, appropriate pH, and tensile stress. That might look familiar to you. Same thing with your stress corrosion cracking. Now, testing monitoring, also smart pigs, hydrostatic pressure tests, direct assessment of the CT. Sulfide stress corrosion cracking is going to be our last type of corrosion that we're going to talk about. It's also found in refinery type environments. High stress, it's the metals that are susceptible are high stress stainless steels, high strength steels, iron alloys. External factors: high temperatures with large amounts of H2S, so it's pretty sour medium going around it. And hydrogen atoms, or when hydrogen atoms are present, that also increase your risk. Mechanism: sulfide stress corrosion cracking is commonly associated with welds, more specifically on just either side of the weld. Atomic hydrogen fuses into steel and causes enrollment of the narrow heat affected zones right next to the weld. In regions of high tensile stress, cracking will initiate. Once initiated, cracks will roll perpendicular to the tensile stress. So you got a load, you got a piece of metal here, and the stress is down here. Here's your weld. It's going to crack going towards your stress. Here's an illustration of it. You can see your iron leaving the steel. And you've got your sour medium out here, your H2S. It's going to come in through here, and you're just going to have your sulfide ions going onto your metal. Excuse me. Stress corrosion cracking, testing and monitoring. Acoustic emissions technique is used to monitor the cracking of steels immersed in a sour medium. So you're going to put it in H2S, wet H2S gas. Prevention: you're going to avoid hydrogen sources, control stress levels, so try not to put more stress than the metal can handle on it. And you can apply post-weld heat treatments to help out with the atomic hydrogen diffusion. And that's it. So we went over 6 types of corrosions. We had hydrogen blisters, hydrogen enrollment, hydrogen-induced cracking, stress corrosion cracking, and neutral pH, stress corrosion cracking, high pH, and sulfide stress corrosion cracking. And all of those things are remarkably similar and have something to do with one another, and they're all categorized under the environmentally assisted